cases. One is embedded SoCs, where hardware vendors just take a bunch of chipset blocks and smash them into one piece and try to sell that. And so we have like a different video pile, we have different GPU, we have display engines to scan and blind things, we have encoders, we have camera capture modules, and they all kind of work different, they all have different drivers. I mean, we have the DRM drivers for GPUs, we have, well, mostly binary blobs and stuff like that. We have video for Linux drivers, we have special purpose encoding and decoding engines, and they kind of need to work together because copying is out of the option, because all the embedded platforms are so bandwidth constrained. And one important thing for the embedded use case is that we need to be able to support the naming reconfiguration, because imagine a camera app where at the beginning you just stream the picture feed from the camera onto the display and you don't do anything in between. And then you play, you press the record button, and then we need to plug in the MPEG encoder to kind of record the video stream, or maybe we need to plug in the GPU to do still picture processing and shortening and that kind of stuff. So the embedded use case is very much needs dynamic reconfiguration of that entire pipeline of how we feed that memory around. This sharing of buffers for this is also very much useful on the desktop. One use case is wireless display, where your display output isn't connected to the GPU anymore, but gets encoded, I think, with an MPEG stream and then put out over the Wi-Fi chip. And of course, multi-GPU, kind of if you have more than one GPU, you need to have some means to move the memory from, or the pictures from one GPU to the other. And that's better done without copying. And especially, also general purpose GPU computations, where you move a lot of stuff between the CPU, GPUs, maybe also some special purpose asset for other things. So on the desktop, the use case is more, the special thing is more that we deal with a lot of buffers. So this problem obviously has a lot of use cases. It obviously already works if you're looking at an Android phone. So solutions, we have Ion and Android ICS. We have like, I think 4 different memory allocators on previous Androids. We have, I think every binary block GPU driver has their own solutions. We have get user pages hacks, which just take some random user space memory and kind of make a buffer object out of that. Almost everyone uses that. I mean, there's video for Linux support. We have stuff for that under the name of WeMap and DRM. So the thing is, there's no common solution. So Linora, or a lot of people around Linora, kind of started to look into a common upstream solution. That work started about a year ago and under the name of Dma-Buf. And just recently, for kernel 3.3, Dma-Buf version 1 was merged. So let's look what we're thinking there. Well, in our great wisdom, we figured out that a buffer object better have a fixed size because it makes things easier. And file descriptors are pretty nice handles for user space. That's like the result of 1 year of work. So, basic pieces. Are you nuts? Like, how am I supposed to create such a buffer? Or allocate his memory? Or backing storage or whatever? The other thing, I mean, having a size is pretty interesting, but what's all going on with the other metadata? I mean, bit for Linux has like sprites and buffer format descriptions and 4cc pixel format layout. And the third point is storage parameters. I mean, these embedded chipsets, they're pretty insane, and you have to be really careful that you allocate the memory in the right place for the right chipset. Some demand contiguous memory, other kind of need one half in this memory bank and the other in the other memory bank, because otherwise memory bandwidth will not not be enough. So to explain that, let's just look at how Dma-Buf version 1 looks like, how it's supposed to be used, and then I'll try to explain why all that stuff is necessary. So from user space, I mean, I'm a kernel programmer, I don't know how user space works, but the first reason why creating an allocation is missing, we thought we have all these subsystems already dealing with buffers. We have DRM bit for Linux. So why don't we just take a buffer from one subsystem, export it, create an FD Dma-Buf handle, and then user space can go walk around and give that buffer handle to every other subsystem, kind of import it on the other side. And this is the way we establish buffer sharing. So the reason why there's no create function is that we kind of reuse all the create functions that are already there. And the verb from user space side that is required to enable Dma-Buf buffer sharing is just to expose the export and import side in an ioctl command. So let's go down a little bit and see how the importer got somehow such a Dma-Buf. Now the first thing it does, before you can actually use it, it needs to attach its device to the Dma-Buf. And you get such a Dma-Buf attachment, and then you can use that one to actually map and unmap the backing storage into the address space of your device, not the CPU address space, but the one that the device says, and actually do DMA with the device sides. So let's address a few of the questions. I mean, that kind of previous slide kind of answered the question why we don't need to create. So why only size for metadata? And one important reason is that other metadata is simply unknown in many subsystems. For example, all the DRM subsystems kind of have no idea what data you're actually storing. So the kernel doesn't know. So the decision was kind of all that other metadata, we need to have something in user space to pass that around. For example, if you have like a video for Linux buffer, which is a special pixel layout, and then you want to display it with KMS, user space has to tell KMS, well, this is a YUV buffer for planes and stuff like that.
Oh, but obviously user space will get it wrong, like most of the time.
Yeah, but that's kind of not my problem. Because yeah, that's one of the last slides. There's a lot of stuff still to be done in user space. We probably need an EGL extension to hide that into the GPU in the Mesa drivers, so that user space can't get it wrong, because it will. The other thing is kind of, we simply wanted to dodge that bullet because a lot of metadata is inconsistent. I think Jesse Barnes can tell a lot about 4cc. And it's simply not required. I mean, if in the kernel side we want to do DMA, and for that we just need a size to know how big. Now the next question, on the previous slide, there was this attachment. I mean, currently in all the DMA APIs in the kernel, you allocate your memory and you just map it, and that's it. Now, Dma-Buf is very much inspired by all these DMA IDs, but why do we need this attachment? Now, as I already said, devices, especially in embedded platforms, have a lot of insane constraints, and we kind of don't want to allocate the memory always for the worst case, because the worst case is kind of contiguous memory, and that's awful to handle. So the other thing is we need to be able to support to dynamically reconfigure the pipeline. So by attaching devices, the importer is tell the exporting subsystem what devices that are participating in the current pipeline, and the exporter can look in the device struct what they actually need. And if a new device shows up and the buffers aren't allocated in the correct way, we can reallocate and move the memory around it. So all this attach and detach stuff is kind of to make the ARM people happy. The last thing, which is kind of special, is the mapping and unmapping is in the device address space. So the CPU can actually access a Dma-Buf on the importing side. And there are a few reasons for that. One is backing storage might actually not really exist in a traditional sense. If you have, like, Dma-Buf has a tiling engine which layouts the memory for optimal 2D accessing patterns, and there kind of the concept of backing storage doesn't really make sense. So to support that kind of stuff, you want to pass or directly return a mapping into device space. The other thing is it's just kind of a little bit more consistent with the MA API. You have a handle for an abstract backing storage, EMA buffer or whatever, and you map that, and that's what you get in return. And the last thing is kind of the importer side shouldn't need to deal with all this storage parameter nonsense, because at the moment the ARM SoCs platforms are getting reworked so that all this complexity about contiguous memory and banks and stuff and all this nonsense is hidden behind the DMA API, so that you can have a driver which runs on one platform and the other, but maybe the memory system works slightly different, and you can use the same driver.
So you always have to have struct pages, right? So in other words, we can't use Dma-Buf for sharing objects whose
Not Dma-Buf version 1.
So his backing store is hidden from the kernel.
Yeah.
For example,
I mean,
content protection
for
services.
for Dave Ellis Prime, just go through the SG table and asks the SG table for the backing struct page, which works kind of for DRM on x86, but nowhere else. But I mean, that's kind of the second part of my talk about missing pieces are CPU access, obviously. We kind of should get access to the backing storage from the CPU side for whatever things. I mean, at the importer side exports a user space API, and user space kind of shouldn't need to know that this is a special buffer object. Everything should still work. The slightly more advanced version of that is we also want to be able to map that buffer into user space, not just access it from the CPU. That's kind of the missing pieces, obvious things. And then there's Dragon, which is eviction support. By eviction support, I mean sometimes the exporter telling the importer get off my buffer, so that it can do like whatever he wants to do with it, move it around. That's kind of the reasons for eviction support. First is buffer movement. I mean, if we reconfigure that pipeline and notice, oops, the backing storage isn't contiguous and we need it now, we need to get everyone off the old backing storage, allocate new backing storage, copy it around, and then tell all the inputs, okay, you can continue now with accessing it. Another reason is swapping support. Gem can actually do it, and it mostly works, which is a bit astonishing. Yeah, or just generally better resource usage. I mean, it's kind of the same reason why we have virtual memory. The kernel just has a much better picture of what is actually getting used and what is just like wasting memory for fun cat pictures and stuff like that. So we can better swap them out if you don't need them, or if the GPU is only a limited window into main memory, you can kick out unuseful stuff. So we want eviction support even for Dma-Bufs. I mean, for simple use cases, we could get by without it, just pin all the memory, and I hope no one else wants to use that memory. But if we kind of look ahead a few years into the more fancy use cases like multi-GPU, we definitely want to support that. And I mean also on smartphones and tablets stuff, if you kind of switch applications with all the multi-threading, the kernel should just be able to kick out things. So how was it solved in version 1? The idea to solve it was, well, we just restrict the time where a buffer is mapped and hence can't be moved, just around the DMA operation. So every time you start like receiving a frame from the video camera and storing it in main memory, you have to call the map, then right afterwards the unmap, so that the exporter can move around the buffer. Now the problem is everyone hates that solution because it isn't really a solution. One problem is on the importer side, all that mapping and unmapping is, at least for a few devices, extremely expensive. So we want to keep onto these mappings for as long as possible. And for the exporting side, all this DMA bracketing actually doesn't really solve the problem. There are quite a few issues still with that, but I'll explain that later on, why it kind of doesn't work. So let's go back to the more obvious missing pieces. First, kernel CPU access. That's currently under discussion. I wanted to write a patch for that, but couldn't get around to it yet. There are a few funny things that we need to take into account. One is we need to be able to support K-map, because at least on 32 bits, the kernel has a split into low mem, which is memory that the kernel can directly access, and high mem. And low mem is just like 1 GB. So in Gem and also in other graphics driver that would use a lot of storage, we allocate buffer objects in high mem, but then we can't access it from the CPU side. So K-map is the infrastructure to get a temporal mapping of one page of that memory into a part of memory where the kernel can actually access it. Usually, I think most video for Linux drivers have always a mapping of the entire buffer. So that's one thing. The other thing which I kind of completely ignored is cache flow. It's a little bit more important on the CPU side, but also all the unmap and mapping for the device side, you need to flush caches. On x86, that problem is pretty simple because usually everything is coherent, at least on the same hardware. But CPU caches, at least on ARM, need to be flushed. And also, if you have the DRM i950 Intel driver, depending on the chipset, we also need to flush the caches so that you don't need stale data, read stale data. We also have to support swapping. Obviously, I mean, if we can swap stuff out, we need to be able to swap it in. But generally, I think it's a rather simple problem. We'll have a solution for that in short order. The next thing is user space nmap support. Now, one big issue is with coherency. as I said, with the CPU access, we need to flush caches. Now a lot of, I think video for Linux especially kind of assumes that user space access is coherent, and also a few other APIs. So what are you going to do with exporters who kind of expect user space to call cache flushing operations? And I think one solution could be if you just intercept the page faults and do the cache flushing behind user space backs. And as soon as we use the buffer somewhere else, we need to shoot down all the PTs. Luckily, we need that infrastructure also for eviction support and swap out and that kind of stuff.
Why not just map it as non-cacheable?
Because you would like it to be fast enough to use.
Yeah, that's kind of.
That doesn't get you coherency with their caches necessarily.
I mean, that's kind of the problem.
Yeah, caches, or if there's GQ caches or whatever.
It actually depends on the architecture as well, because on some architectures you cannot have multiple mappings with different caching attributes. So if you have kernel mapping as cacheable memory, then you cannot have a user space mapping as uncacheable.
Yeah, and as I said, different subsystems kind of have different design philosophies. One thing, okay, we export all that coherency nonsense to user space, and the other thing, we hide it all. So we have to kind of do a mismatch. Yeah, we have to kind of keep that away, or be able to fake a coherent mmap to user space. So there's not much going on there, but I think that problem is pretty much solvable. Maybe we can throw in a crazy extension to expose the coherency and cache flushing to user space so that we don't have to shoot down the PTs. Sometimes that's too expensive. So let's go back to the Dragon. Why is the Dragon a Dragon? There are a few things. One is simple locking issues, which are kind of the easiest one of these three. Then the next one is buffer reservation deadlocks, which is already pretty much fine. And the last one is that we should be able to kind of only hit the OOM killer when SMAP is completely full of gem objects, but it's easy to come up with scenarios where the OOM killer gets angry much earlier. So let's look at the locking issues first. The basic problem is kind of, usually if you map stuff, you come from the importer, go through the Dma-Buf layer and get to the exporter, and everyone in there grabs some locks. Now for eviction support we kind of have to go the other way, and that usually results in deadlocks. But I mean, Dave-Ellis DRM prime work already angers lock depth pretty decently. But I mean, that's a standard problem in kernel engineering. We have solutions for that, from tri-locking to restricting or introducing locks for smaller subsets of the data structures we want to protect. So I say that's solvable, it's just work. Much more fun is kind of buffer reservation deadlocks. So now we have like two subsystems with a few buffers each, and they both use buffers from the other side. And now for some other reasons we have full buffers, but we can only fit 2 into main memory. It's a bit contrived, I know. But now assume we need kind of one buffer from the other side. So first both subsystems put A1 and the other subsystem B1 into main memory. That still fits. I mean, we can put 2 buffers into memory. And then they try to put in the other one that they need. So subsystem A wants to map the buffer B2 into its address space. Ask subsystem B, can you please do it? Subsystem B notices, well, there's not enough space for that. I need to kick out something. And it decides to kick out B1. Is that right? While the other one tries to kick out A1. the other subsystem asks subsystem A to please put in A1, A2, and that tries to kick out A1. So now everyone is waiting for everyone else. I mean, you can kind of throw around the buffer names a little bit and come up with plenty of scenarios. You can also do the same thing with like only one subsystem being the exporter. And then you try to pin both buffers into main memory. And when you try to pin in the second one, the subsystem tries to kick out the first one. So then you dialogue with yourself again. I mean, to make that thing slightly less contrived, just think of the two buffers as buffer sets. Like A1 could be like 20 buffers, and then with A2 we have that one single buffer that is too much. So that actually happens in practice. Or it can happen in practice. I mean, usually your hardware should be designed so that everything fits in for your pipeline and stuff. But I kind of imagine what happens when you switch Windows or something like that. And then suddenly we try to fit two working sets and only one fits. I mean, the thing that should happen is we first run the one subsystem task and then kick out everything and then the second one. So how can we solve that problem? I mean, in a way, it's a classic locking problem with a few locks. So the solution there is usually to kind of impose an artificial ordering and just say, well, you have to start at the lowest address and lock this way up. And if you go the wrong way, you have to use trilocks. Now, that's a bit too simple because that has some pretty decent fairness issues because you usually can't control in which order or it would be kind of a bit of work to control in which order you want to reserve these buffers. So if you're unlucky that the last buffer you want to reserve has a very low ordering, you kind of get starved. So TTM has a very nice solution for that. It creates a global queue of reservations, so every time you try to use some kind of buffer, you get a reservation ticket. You mark every one of your buffers with that reservation ticket before you do anything else, and then you try to map these buffers into whatever resources you have, system memory or some small remapping unit. And then if you need to evict something, you check whether that buffer already has a ticket, a reservation ticket. And if that ticket is ahead in your queue, you know you kind of have an inversion. And you need to back off, drop all the pins on the buffers you need, and then start anew. And because the global queue is ordered, we don't have any starvation issues anymore, because a later task can never get ahead. And the other cool thing is, as long as you don't have to kick out any buffer that already has a reservation ticket ahead of you, everyone can just process things in parallel. So that's a pretty nice solution. The problem is it's currently TTM and not Dma-Buf. Nothing up there. So we probably have a little bit of work ahead to extract that. And kind of the last and hardest problem with the eviction dragon is angering the OOM killer. So we have like two applications, one with tons of funny cat pictures in hidden tabs, so they're kind of just wasting main memory. And the other one, we trying to kind of take a picture or something, we just have a few video buffers running. So now you think, well, we could use this, put the CPU to some good use and start like a kernel compilation. And the thing we want to happen is that we put all these funny cat pictures into swap so that we can compile the kernel. Now the problem is that what's actually going to happen is all these funny cat pictures are mapped into the device space. And the core kernel memory subsystem doesn't know about it. It just sees, oh, this memory is pinned. I can't move that way. So then the core memory subsystem starts the OLM killer, And that also notice, well, we don't have any system RAM memory left because that's all pinned by DMA buffers. So it starts to kill some random processes until probably at the last one it kills your Firefox session, and then suddenly there's a lot of space left. And that's actually what happens in current kernels. So, I mean, that shouldn't happen too often, obviously, and it doesn't happen too often. So we look at a few of the solutions. TTM is pretty simple. It just has a bunch of global pools and limits, which I think currently is half of system RAM, which is a bit pointless. I mean, if you have to buy twice as much memory as you actually need. And, well, DRM i915 solution we can do swapping to is even more simpler. If DRM i950 notices that it can't get any memory anymore, it kicks out a few things itself, which works as long as you only look at DRM i950. But as soon as something else comes around, that something else can't kick away the memory of DRM i950. So even in current drivers, the problem isn't really solved in a satisfying way, in my opinion. And I think that's going to be really fun to solve that with Dma-Buf. But I think we kind of have to solve it because with all these devices that crop up, all these encoders and special purpose ASICs, I think we will have even more use cases in the future. So, that's kind of the stuff I have no clue about, which is user space. What's still left to do? I think I showed you quite a bit what's still left to do of the kernel. So there it's just writing patches. And one thing also extends the DMA API because a lot of these things we need are kindly reinvented in every DRM driver or in a lot of them. And I think with better platform abstraction, you'll end up with a few new interfaces there. And for user space, I've heard noises from Wayland of people that they're looking into using Dma-Buf as their transport because it's kind of just the general thing. As somebody already said, we need some solution in user space to kind of sort out the layout and drive and format and pixel stuff so that user space can actually make a few devices talk together. And I think in the general case, if you don't just try to write a driver that just knows how these things can work together, we need some EGL or GBM, which is the memory management for Wayland extension, where we can say, like, I have this video for Linux device, it can support this and that, make a buffer for that, so that I can display it on the GPU. But yeah, I'm kind of not so much for in that discussion. So, well, it looks like I've rushed through the slides. Thanks a lot, especially to all the people from Lenara, because I haven't actually written any patches for Dma-Buf. That was all the work of Summit Civil and Rob Clark and a lot of other people. I'm just kind of yelling at them in the mailing list if they come up with ideas that then quite work with DRM. Yeah, questions?
So I'm interested in interfacing FPGAs to ARMs, and I've got a driver that uses DMA to suck data out of an FPGA and puts it into a large buffer that we memory map to the user. So this is very interesting to me. Is this the sort of audience that Dma-Buf has?
Well,
non-display oriented applications?
the thing is, if you just have one driver, you kind of don't need Dma-Buf to share it with something else. But assuming you have something else.
Well, I'm sharing the user space, so.
Well, the current DMA API can already do that. Should be able to do that. I mean, that works.
I mean, I have, you know, I basically copied a ring buffer allocator out of the Ethernet driver to get something to user space directly. I mean, the problem I had was getting into user space.
So you're talking about still having all the Nmap handling in each particular driver, right?
Yeah.
You're
I
not
mean-
exposing a new Nmap handler from Dma-Buf.
Well, maybe we'll expose a new Nmap handler for drivers, so that they can implement Nmap for whatever fancy use space IOCL they have. And I mean, yeah.
Yeah, so it sounds like you don't need the Dma-Buf infrastructure for your case yet, but if you wanted to take those ring buffers or some of the data that was emitted by the FPGA and wrap it into something that could be consumed by another driver and then share at the user space level, then you'd want to look at it. But at this point, it sounds like there's just overlap between some of the things Dma-Bufs do internally in terms of the page pinning and whatnot and what you need to do, but not necessarily that you would need to use this subsystem yet.
Well, I think it's just yet, from the importer side, it's just yet another kind of DMA API, like you can wrap struct pages into DMA SG titles and map that, or you can allocate coherence DMA memory. And now there's just like a new kind of DMA thingy, which is called Dma-Buf, and you get that from user space with this file descriptor handler. There was a question.
Yeah. So, tell me how